Let's discuss why is it that when a complex number is the root of a polynomial, then automatically the conjugate of this complex number will also be the root of the polynomial. So for a polynomial in general, let me write it as fz to be equal to the coefficient of the highest powered term in the polynomial. Let me go for a0, then z to the power of n. And the next term, a1, will be for the second highest power, so z to the power of n minus 1. And if I were to go all the way until the second last term, the coefficient can be an minus 1, and it is going to be just multiplied to z. And the very last term will be the term that is independent of z, so it will just be the coefficient itself, so an. So this is the polynomial, and I'm going to assume that w is the root of this polynomial. So I'll let w, which is equal to x plus iy, be the root of this polynomial fz, and this will imply that fw should be equal to 0 since it is the root of this polynomial, which also means that a0 w to the power n, replacing all the z's by w, then plus a1 w to the power n minus 1, all the way until an minus 1 w plus an, this is equal to 0. And the next thing that I want to try do is to bring in w conjugate. And to do that, I'm going to take the entire left-hand side and I'll try to do a conjugate. And that is what I'm going to do to the right-hand side also. So on the right-hand side, it's going to be 0 conjugate. On the left-hand side, it will be a0, w to the power n, plus a1, w to the power n minus 1, all the way until an minus 1 w, and an, the whole thing will be conjugate. So on the right hand side, 0 conjugate, let's think about it. It is a real number conjugate. Let's do a quick test. So if I have a real number conjugate, I can also rewrite this real number as if it is a complex number, 3 plus 0i conjugate. So what is 3 plus 0i conjugate? It is going to be 3 minus 0i, which is actually going to be equal to 3. So based on this, we are going to deduce that if I have a real number and it is being conjugate, then it is just going to be the same. Okay, there's going to be no change. So 3 conjugate is still going to be equal to 3, which means that 0 conjugate is still going to be equal to 0. So I'm going to write this here for the right-hand side. As for the left-hand side here, we need to use some algebra or some rules of conjugate. I have shown you this before in class, so let's just make use of the rules directly, okay? For example, if I were to make use of the very first one here, the very first one will help me to change this into a a0 w to the power of n conjugate, then plus a1 w to the power n minus 1 conjugate, then this will be an minus 1 w conjugate, then plus an conjugate. And then if I were to make use of number 2 will change this to a0 conjugate, then w to the power of n conjugate, and this will be a1 conjugate, w to the power of n minus 1 conjugate, and all the way until this, which will also be an minus 1 conjugate, w conjugate, plus an conjugate. This is equal to 0. And if I were to then make use of number 5 over here, this one, if I were to make use of number 5, then wn conjugate will be w conjugate to the power of n. The coefficient will remain as this, and this will be a1 conjugate, this will be w conjugate to the power of n minus 1, and all the way until this will be an minus 1 conjugate, w conjugate, plus an conjugate. This is equal to 0. And I have not deduced anything if I were to just look at this as what we are looking at on the board. But what if there is a condition that is being imposed to this particular polynomial? And specifically, that will be for a0, a1, all the way until an minus 1 and an. What if all these coefficients happen to be real number? Then we actually will get a very interesting result, which actually we are trying to prove that. So let me impose this condition to our polynomial, okay? So if all the coefficients, which are going to be a0, a1, and all the way until the second last coefficient, which is an minus 1, and the last coefficient, which is an. If all these are real numbers, and according to what we have discussed, real number conjugate is still going to be real numbers, which means that a0, if it is a real number conjugate, it is still going to become a0. then this will be W conjugate to the power of n. A1 conjugate will be A1. Then we have a W conjugate to the power of n minus 1 all the way until here, which will be still an minus 1. Then W conjugate, and since the coefficients are all real numbers, this will remain as an. This is equal to 0. And can you see what that is here? What that is here is actually this, except that Z is replaced by W conjugate, which means that I can actually rewrite this entire left-hand side here with that notation, which is F W conjugate, and this is equal to 0. And what have we gotten here? If F W conjugate is equal to 0, this will imply to us that W conjugate is a root of Fz. And that is why if W is a root of the polynomial, provided that all the coefficients of these polynomials are real, then W conjugate will automatically also be the root of the same polynomial.